Welcome to Quantum Computing Unlocked. Today, we're diving deep into the fascinating world of qubits. By the end of this video, you'll have a solid understanding of what qubits are, how they work, and the different types used in quantum computing. Let's get started. First things first, what is a qubit? Unlike classical bits that can be either 0 or 1, qubits can exist in a superposition of both states at the same time. This unique property allows quantum computers to process massive amounts of information simultaneously, far beyond the capabilities of classical computers. Imagine a qubit as a spinning coin, not just heads or tails, but something in between as well. This superposition is what gives quantum computers their incredible potential. Now, let's explore the different types of qubits used in quantum computing. We'll cover 5 main types: superconducting qubits, trapped ion qubits, topological qubits, photonic qubits, and spin qubits. First up, superconducting qubits. These are the most common type used in current quantum computers. They use superconducting circuits cooled to extremely low temperatures. When cooled, these circuits can carry current without resistance, allowing them to represent qubits. Companies like IBM and Google use superconducting qubits in their quantum processors. These qubits are manipulated using microwave pulses, allowing precise control over their state. The main challenge here is maintaining the delicate superconducting state and reducing error rates. Superconducting qubits operate in dilution refrigerators that reach temperatures close to absolute zero. This environment is necessary to maintain the superconducting state and to minimize thermal noise that could disrupt quantum operations. The circuits themselves are made from materials like aluminum or niobium, which become superconducting at these low temperatures. Next, we have trapped ion qubits. These qubits use ions, which are atoms with an electric charge. The ions are trapped in place using electromagnetic fields. Lasers are then used to manipulate their quantum states. Trapped ion qubits are known for their long coherence times and high fidelity. Companies like IonQ and Honeywell are pioneering this technology. The process of trapping ions involves creating a vacuum chamber and using electric and magnetic fields to hold the ions in place. Lasers are then used to cool the ions and to manipulate their quantum states, allowing for precise control and measurement. In more detail, the trapped ions are usually cooled to near absolute zero using laser cooling techniques. Each ion can represent a qubit, and quantum gates are implemented by applying laser pulses that induce interactions between the ions. The challenge with this technology is scaling up the number of ions while maintaining control and coherence. Moving on to topological qubits, which are still largely experimental. These qubits rely on exotic states of matter and are designed to be more resistant to errors, thanks to their topological nature. Microsoft is heavily investing in topological qubits, hoping they will lead to more stable and scalable quantum computers in the future. The idea behind topological qubits is to use quasiparticles called anyons, which exist in two-dimensional materials. These anyons exhibit braiding properties that make the qubits more robust against local disturbances, thereby reducing error rates. Topological qubits are formed in materials that exhibit special quantum states, such as fractional quantum Hall states. These qubits leverage the braiding of anyons, where the quantum information is stored in the collective state of the system rather than in individual particles. This approach promises greater fault tolerance, which is crucial for building large-scale quantum computers. Next, we have photonic qubits. These qubits use particles of light, or photons, to carry quantum information. Photons are advantageous because they can operate at room temperature and can be easily transmitted over long distances. Researchers are working on integrating photonic qubits into existing fiber optic networks, which could revolutionize quantum communication. Photonic qubits can be manipulated using linear optical elements such as beam splitters and phase shifters. The main challenge here is generating and detecting single photons with high efficiency and fidelity. Photonic quantum computing often uses entangled photons generated through processes like spontaneous parametric downconversion. These photons are then guided through optical circuits that implement quantum gates and measurements. The ability to easily transmit photons makes this approach ideal for quantum networks and secure communication. Lastly, spin qubits, which use the spin of electrons or nuclei to represent quantum information. These qubits can be implemented in materials like silicon, making them potentially compatible with existing semiconductor technology. Companies like Intel and academic institutions are exploring spin qubits for their potential scalability and integration with traditional electronics. Spin qubits are controlled using magnetic fields or electric fields in combination with microwave pulses. The primary advantage of spin qubits is their compatibility with existing semiconductor fabrication techniques, which could allow for easier scaling. In more detail, electron spin qubits are often created in quantum dots, which are tiny semiconductor structures that confine electrons. Nuclear spin qubits, on the other hand, use the spins of atomic nuclei within a solid material. These spins can be manipulated using nuclear magnetic resonance techniques. The main challenge with spin qubits is achieving and maintaining coherence over long periods, especially as the number of qubits scales up. To recap, we have explored superconducting qubits, trapped ion qubits, topological qubits, photonic qubits, and spin qubits. Each type has its own advantages and challenges, and researchers are actively working on developing these technologies to unlock the full potential of quantum computing. Quantum computing holds the promise of revolutionizing fields from cryptography to materials science, but we are still in the early stages. The diversity of qubit technologies highlights the experimental nature of this field and the exciting possibilities ahead. Thanks for watching. If you enjoyed this video, don't forget to like, share, and subscribe to B2Q Innovations for more insights into the world of quantum computing. Stay curious, and see you next time.